Thank you for joining this webinar from the Engineering Integrity Society. I will now hand you over to today's host, Graham Hemmings, for an introduction to today's presentation and the Society.
Right, good afternoon, everyone. Welcome to this webinar. The Engineering Society is a non-for-profit organisation. Some of you, perhaps a lot of you, are members already, but the Society consists of four main groups: simulation, test and measurement, durability, fatigue, sound, vibration and product perception group, and the Young Engineers Forum. We run seminars, exhibitions and conferences, and it's all aimed to benefit engineers who are out there doing the job at the moment. As a matter of interest, Tryggvi is going to talk about the work that they've been doing with the Formula Student racing car, and the EIS has been sponsoring Wolverhampton University for the past 5 years, perhaps 6. Just not quite sure about the start date, but we've been closely looking at their developments, and they've made great progresses over the last few years, and Tryggvi's work is going to, I'm sure, help towards that in the future. We've got many corporate members. We rely on corporate members for their sponsorship of our own organisation, and you can see there that they're quite high profile companies that help us towards delivering our objectives. So without further ado, I'll just go on to the last piece of information regarding the Engineering Society. As I said, we hold seminars, exhibitions and conferences, and if you need any more information about those, they're always available on the EIS website, or you can contact Sarah directly to get any further information. So I'd like to hand you over now to Tryggvi, and I'm sure you'll find this presentation very intense. I've looked at it myself and I'm very impressed with the way he's put it together, and so I'll hand over to Tryggvi now. He'll introduce himself and the work that he's been doing. Okay. One last thing, you'll obviously hopefully have some questions to ask Tryggvi towards the end of this. I'd ask you to keep them to the end so that we can direct them and manage them in a better way. Okay, I'll close my camera down now and hand you over to Tryggvi.
Thank you very much, Graham. Let me just quickly get the presentation up and sorted. Right, now everyone should be seeing the title slide. Yes, as Graham and Sarah have mentioned, I'm going to be doing a bit of a talk on suspension analysis and tuning. The sort of primary focus about this is going to be the work that the University of Wolverhampton's Formula Student team has done with the Multimatic facility down in Thetford. But just as a brief agenda, I'm just going to have a bit of a personal introduction about myself, then just going to give a bit of background information on the university and the Formula Student program here as well. Then we start to get into the sort of more hardcore aspects, going into the fundamentals of suspension design and analysis. Then we're going to look into the Multimatic 4-post test rig and their vehicle dynamics center down in Thetford. Then I'll give you a bit of a sort of summation of the procedure of the day and what our findings and improvements were that we made on that day. I'm also going to give you a little bit of a talk about what's going to happen from here on out, and then at the end we're going to have a Q&A session. So without further ado, on to myself. My name's Tryggvi. I joined the University of Wolverhampton for the 2020/21 academic year. I'm currently studying a BEng in motorsport engineering, and I'm in my final year at the minute. My main area of specialization and interest is suspension and vehicle dynamics. It does sort of make me out to seem like I'm a professional at this, but I'll sort of iterate that I'm by no means a pro at this. I've only been really studying it in any sort of depth for the past 3 years. And there are people who've been studying it for far longer, and they know a lot more than me. But this is just going to be sort of a summary of what I've learned in this process of doing a suspension system for an FS car and then taking it to Multimatic. And my current role at UWR Formula Student is the lead suspension engineer. I've also done a little bit of racing myself in my spare time, not so much now that I've been at uni because it costs a lot of money, but I'm planning on carrying on with that once I've left. So just a bit of a history of the uni first off. In 1827, the Wolverhampton Tradesmen and Mechanics Institution was founded. This then throughout the years had more and more schools added onto it, and it sort of merged together with the College of Art in 1969 to form the Polytechnic here. Then after a number more years of operation, the Polytechnic was granted a university status, and the university as we know it is born. We've got 3 campuses here at the uni as well. We've got the primary campus in Wolverhampton, named the City Campus. You've got primarily the maths, sciences, businesses and humanities courses there. The Walsall campus is more oriented towards sports, health sciences and teaching. And there's the campus which I'm based at, which is the Telford campus. This is where all of the engineering studies happen and the majority of adult nursing and paramedic courses are as well. We've got a number of facilities here as well. This is sort of prevalent for the University of Wolverhampton project, especially. The Formula Student project. The majority of these facilities are accessible by students, and those being a wide variety of milling machines and lathes, CNC machining, and we also employ a lot of ALM processes for 3D printing different metals. We also have quite an extensive composite lab as well, and we utilize a lot of normal plastic 3D printing for our rapid prototyping stuff as well. The Formula Student project here at the uni was originally founded in 2014, and it's been running ever since really. The best finish that the uni has had was in 2017. Where we managed to finish 13th overall out of the 100 plus entrants, and we were the 9th place UK team, which I think is pretty impressive considering some of the competition that we were up against. Last year we changed up the format of our team. We've changed into a 2-year rolling program now, where we spend a year doing a concept entry, and then the year afterwards we enter the actual car and try and race it. We finished 10th in the concept class last year, with a 5th place finish in the costing. We only narrowly missed out. We missed out on the costing finals by I think 10 or 15 points, but we took that as sort of a main area of improvement in that regard, and we're looking to get into the costing final in this year's one as well. And of course we are always aiming to beat the university best finish, but especially so going into the 2023 season. The main reason I like Form a Mueller student here is it gives a good avenue for students to put their studies into practice as part of a actual engineering challenge. But it's also got that sort of freedom to make mistakes. So you aren't costing someone millions and millions of pounds by making a part wrong, say. But it's sort of a very good avenue to sort of get you into the habit of running and operating a relatively large scale engineering project as well. And all students from all engineering disciplines are encouraged to join here. So it's open to everyone, really. The Wolf 7 is the current iteration of the car. Just some key specs and performance metrics for you. We're running an internal combustion car with a Yamaha YZF R6 engine. This powertrain is looking to be replaced for the next year and the year after, I believe, but that's still in talks at the minute. We run a steel space frame chassis as opposed to a carbon monocoque. This is mostly a cost thing and sort of a knowledge foundation, really. But we've managed to do a bunch of optimization on it, so we've got the mass down to only about 31 kilos, which I think is pretty impressive. And we're targeting 200 kilograms of mass, which is not including the driver. We're estimating a 0 to 60 time of 2.8 seconds, which seems really, really quick, but when you consider it's a motorcycle engine in something that's only going to weigh about 280 kilos, it sort of starts to make sense. And our top speed is going to be around 78 miles per hour. Then our peak lateral acceleration is going to be in the region of 1.5 Gs. This of course is based on empirical tyre data, and a lot of the testing procedures around that aren't very reflective of a real road surface. So that's sort of a broad estimate. Coming back onto what the former student competition's about, it is effectively just an engineering challenge. I've seen it described as an engineering business exercise where you get to make and race a car on the side, which doesn't really make it sound that interesting, but it's very much a culture there too. When everyone shows up at Silverstone for the week-long event, everyone's there just to help out, and it's all just it's effectively a collection of students with one goal in mind, which is just to finish it, which often ends up in some quite strange scenarios. I remember in 2021, Coventry and I believe Salford had a bit of a collision coming out of a hairpin, and there was this big scramble for Salford to repair their car and finish the endurance event. But yeah, they won the Spirit of FS's award that year. In terms of what we have to do at the event, it's split into two categories. We've got static events and dynamic events. The static events are very much paperwork and theory-oriented stuff. So we get judged on our engineering design principles and our knowledge of how, well, it's mostly why we made the car the way we did. And we also get judged on the costing and manufacturing side of things, making sure that all of our costs are captured accurately and reasonably as well. Then the final static event is the business plan and presentation, where the IMechE give us a business case where we have to make a presentation around it, and then pitch this idea to them, and this goes through all of the financing aspects of an engineering challenge as well. The dynamic events, which are the thing that we all sort of do as the fun part, assuming the car makes it through scrutineering, which is often a very big challenge on its own. We've got the acceleration, skid pad, autocross, and endurance events. Acceleration is a 0 to 100 meter dash in the fastest time possible. Both drivers get 2 goes each, and it's a similar case for the skid pad, but it's a figure of 8 configuration, and they time how long it takes for you to complete both rings around each side, and then they give you an average time based on that completion time. Autocross and endurance use the same track. The difference being autocross is a 1-lap sprint, go as fast as you can, get the fastest time possible type deal. Whereas the endurance is very much a test of how strong your car is and sort of all of the engineering practices which you've put in to make it last as long as you can. That format is 27 laps, I think it was last year, going around the same autocross circuit with a driver change in between. But but that tends to be where a lot of the cars conk out, because the prototyping process for making these cars often yields a vehicle which is good for one, if like say one use cycle, but going through that same cycle multiple times, various things such as fatiguing in components starts to happen. It tends to be the car killer, really. So that's sort of an overview of what we have to do each year at the Silverstone event. So going on to the meat and potatoes of all of this, really, starting off with why suspension is so important for a competition vehicle. For a lot of you, this first statement is relatively obvious, but it is the physical link between the car and the road, and ultimately it's the link between the driver and the road surface as well. The reason why I say it's the suspension system is the link between the car and the road is because the tyre is always considered as part of the suspension. I'll go into more details as to why later, but there's also the very important point of any outputs from other vehicle subsystems. They act as an input into the overall suspension system as well. This could be things such as engine vibrations, steering movements, sloshing of fuel inside the fuel tank as well as a common one. But every single subsystem on the car has some sort of bearing on how your suspension acts. It just sort of depends in what reference frame you're going to analyze those effects, really. But I think the most important reason as to why suspension is used is that it allows for control over vehicle body and wheel movements. And I emphasize the aspects of control because if you can basically say how you want the car to act in any given condition, it sort of pays into having your driver having a bit more confidence in it, and you know exactly what's going to happen, and it allows for mathematical modeling of setup changes and variations depending on what conditions your car is in, say. But that then poses the question, how do you define a good suspension system? I think it's pretty obvious to say that it depends entirely on the context and the use case of the vehicle. For instance, in the case of a motorcycle, a good suspension system usually gives the rider a lot of confidence in the front end on the brakes and its ability to, in quotes, hold a line. If it fails to do those two things, they tend to be not very confidence inspiring, and the rider doesn't really like to get on with it. But when you compare that to something like a GT3 car, say, you're more prioritizing stability on turn-in and whether you would prefer an understeery setup or an oversteery one, and then also stability on corner exit as well. If you're starting to oversteer as soon as you put the power on, you might not gain a lot of confidence out of that. But some drivers do like that. So that's sort of where the subjective side of things come in. But in terms of the context of motorsport, I think you can summarize what a suspension system can do quite concisely by effectively saying it has to maximize the tire grip, because that's ultimately what sticks you to the ground and makes you go faster. It should adequately support the vehicle around the track. By that, I mean it's not grounding out on the belly pan constantly. You do see this in F1 where they are sort of skipping along the ground down the straights, but they've got the systems in place to mitigate that, and the engineering around the aero system on those cars is sort of made to do that on purpose almost. Have good stability and predictability is a good one, and providing a sense of feel is important, because a bad suspension system can make the vehicle feel almost numb, and you don't really understand what the tires are doing, and it's very difficult to feel how the car is reacting to certain sections of the circuit. But as I mentioned, the most important thing is to give the driver confidence, because as the driver's the one in control of the vehicle, it's it's ultimately down to them to make it go fast. So yes, you could have a theoretically perfect suspension system, but for the most part, those systems tend to feel quite wallowy and vague, and again, quite numb. So drivers don't tend to like that. But this is where splitting optimization of a suspension system into two components sort of comes into play here. I tend to sort of phrase it in the form of objective performance and subjective requirements. Objective performance is the sort of guidelines to what a good suspension should contain. And this doesn't really change. It always acts as a solid foundation for the driver to build on. This is usually changing things like your spring rates to get them dialed into an approximately correct state, changing your aerodynamics as well. That can have a bearing on the suspension, and usually it's quite a big bearing on it. And then getting a good baseline for your damping rates and constants is sort of the key to making an objectively good foundation for your suspension. Where it then strays into subjective requirements is where you're starting to tailor the suspension for a driver. So this can be changes like anti-roll bar tensions, minute changing in damping constants, and just the really small things which you tweak to sort of to give the driver confidence and have the car feel the way they want it to feel. And it's that human element which is sort of one of the biggest factors in setting up a vehicle for motorsport as a whole. Is just to make sure that the driver's comfortable with pushing it up to that very limit. But that sort of summarizes why suspension is really, really important, and the impact that the driver or the person in control has too. Before going any deeper, I want to sort of give a quick note to geometry as well, because this is a very important factor. And as a word of warning, from here on out, all of the suspension analysis and terminology is going to be in the context of a four-wheeled car. When you start to try and do suspension analysis for motorcycles, it gets a little bit complicated, because you've got the extra degree of freedom being the leaning left and right, and your tyre characteristics tend to change a lot too. But for the most part, you can identify a lot of issues in your suspension setup from your geometry. It's a bit harder if you're in a production vehicle of some sort, say if you're in a GT3 car and Audi have given you their new Evo 2 R8. But if you've got a way of sort of managing to plot out your three-dimensional geometry in space, you can then do a series of 2D sketches in the front and side views to sort of get an idea of how the stability of the geometry itself is affecting your suspension. But the main indicator to stability is usually the roll center location and how that changes in given conditions. The first point, and this is more from a design aspect, is having your roll center too high. It can lead to jacking, which is effectively when the car enters roll, it will try to pick itself up almost, and it will start to reduce tire loads on the outside tire, and then your grip starts to sharply fall off at that point. But it also can lead to excessive lateral tire scrub when it's going through its bump and droop. That's got more of a tire wear impact, and it's not really ideal because, as you can imagine, on a track, the car's going through bump and droop very, very fast for hours and hours and hours on end. So having a characteristic which is going to negatively impact your tire wear isn't going to be very beneficial if you're trying to contend for the win, say. But then having it too low at the same time, that can lead to excessive body roll because the actual roll center at that point is disjointed from the center of the body itself. So it's almost like it's traveling on the outside of a circle, and that circle is quite far out from your roll center. But this can also lead to increased roll couples, which means that to account for them, your suspension stiffness in roll has to be far higher. And generally, if you're trying to analyze an existing geometry, if your roll center deviates a lot with small changes in roll or in bump, that's a good indication that your geometry is not very stable. The perfect geometry, which isn't really attainable, would have the roll center stay in exactly the same location through bump, droop, and all roll. And in pitch, it would sort of stay at the same point relative to the body. And generally, you don't want the roll center to move below the ground plane during roll. This has a number of effects, but specifically, it creates an instability. And it's got to do with summating moments around the roll center. I've not got many notes on it here, but there's a good book by Derek Seward called Race Car Design, and that basically summarizes the majority of suspension principles quite nicely in there. So moving into the fundamentals of trying to suss out what your suspension is doing. Empirical analysis is mainly used to identify weaknesses in an existing setup or geometry. And it serves to give sort of a window of performance. By that, I mean, it gives you a broad region in which your car can operate well, but you can move inside that window for your adjustments to sort of tailor how you want the car to feel for each driver. And that sort of harks back to that point of making a good setup at first, but then tuning it for each driver as well. Primarily, the suspension is analysed in modes of oscillation. The three ones pictured on the screen there are heave, pitch, and roll. Heave is effectively all four wheels moving vertically in unison at the same time. This is sort of analogous to sort of undulating road surfaces. For instance, take turn one at Brands Hatch going down Paddock Hill Bend into the compression. That will sort of compress all four wheels identically at the same time, and that can sometimes result in a fair amount of shock vertical loading if it's not set up correctly. Pitch oscillations are to do with braking and accelerating. So again, it's sort of taking Brands Hatch as an example. If you're going uphill and then into turn one and you're hard on the brakes just after the pit lane exit, you're going to be experiencing both heave oscillations because you've got that slight rise in the track, and then your pitch oscillations are also happening on the front end too. Then roll oscillations, of course, they're quite self-explanatory. That's when you're cornering. There is a fourth mode which is analysed at Multimatic called warp. That's a quasi-static analysis of opposite corners of the car going through bump and droop. This is usually used to measure chassis torsional stiffness if you've got a solid link in there instead of a damper, but it can be used to quantify the effects of anti-roll bar tension changes too. There's a lot of complicated maths around warp analysis, which I'm yet to sort of delve into, but yeah, that mode is especially useful. Mainly if you don't know what your suspension and chassis stiffness ratio is, that tends to be an indicator as well of how stable your suspension's acting in those modes. Now moving on to actually modelling the car itself. A race car is effectively four corners which can be distilled into a system of two weights. You've got your sprung mass on the top there, which is supported by the damper and the spring. Then you've got your unsprung mass, which is effectively the mass of your wheel assemblies and a portion of the suspension linkage as well. That is supported by the tyre. Now, there's a lot of simplifications and assumptions that have to be made for this. Namely, you want to state that your sprung mass is constant at any given moment. As it's being analyzed in sort of in sort of a snapshot, you are unlikely to get any deviation in your sprung mass due to fuel consumption, say. But also you want to make sure that your damping constant doesn't change. While in reality it does due to friction inside the damper and such, it's a comparatively very, very small amount. For very simplifying reasons, the tire is represented by a linear spring of constant stiffness. If you wanted to get a completely mathematically accurate model of the tire, it's near enough impossible, because you'd be analyzing every molecule of the tire, and there's probably some quantum physics in there somewhere stating that you can't really do that. But yeah, that sort of is required to make it simple, and many sort of approximating tire models need an extraordinary amount of computing power to actually solve. And when you've only got a day to test your entire car there, it doesn't make sense to be running it through this extremely complicated like this. It's sort of very, very hard to get the work done fast, really. But the linear spring model is accurate enough to give you a really good idea of what's happening. And the last assumption is that the system obeys simple harmonic motion. This is just because it is ultimately masses and springs acting in the same way as a pendulum does. A note on excitations is needed as well. There's two types. There's direct and indirect. The direct one is a displacement of a mass in this mass spring damper system as a result of a force acting directly on it. The indirect one is caused by a displacement in the ground plane in which it's connected to. If you see diagram B there, that's the one of most interest because that most closely resembles a road surface. Additionally, the displacements can be expressed in two ways. You can express them as a step input, which is useful for analysing one-time sort of recovery periods of your suspension from, say, a pothole. But the more powerful tool is a sinusoidal input, which effectively acts as a bunch of frequencies which act on your suspension. Because if you model linear displacement in the form of well, in the context of simple harmonic motion, you can get a sinusoidal input from that, and those sinusoidal inputs are the main focus of what Multimatic do at their Vehicle Dynamics Centre. Speaking of, let's go into a bit of information about this. Their Vehicle Dynamics Centre is located in Thetford in Norfolk. They've also got one in Ontario. I can't remember exactly where in Ontario though, but they are primarily an American-Canadian company, so they operate more heavily out of there. There are 3 available facilities. There's the 4-post test rig, which I'll be going into. There's a driver in the loop simulator, which takes data gathered from the 4-post test rig and simulates your vehicle with laser scan track data, so it can create a relatively accurate response and simulate exactly what the car is going to do based on the parameters you've found on that 4-post test rig. Then there's the K&C testing facility. That K&C stands for kinematics and compliance. This is useful for when you're trying to analyze tolerance-based systems and identify the real-world factors of safety in a car, which is what you can see with the Mercedes on that big yellow rig there. Some information on the 4-post rig itself. It consists of 4 hydraulic actuators, which support the wheel mass of the car. Each actuator has 3 load cells per pad, a linear encoder to measure the displacement of the hydraulic actuator, a single axis accelerometer to measure the up and down accelerations, and it's got 3 magnets on the base just to help make it easy to place them in exactly the right place for varying car sizes. There are 2 additional actuators which have cables that pull down on the front and rear of the car if you wish to simulate downforce as well. We didn't do it for our car because we don't have a very big aerodynamics focus. All of the actuators are controlled using a bespoke controller, which was developed by Dave Williams at his time at Cranfield Uni. The rig controller currently in use is from a Lotus Active Esprit, but it's just been flipped upside down, and values have been accounted for to account for the fact that it's been flipped upside down. At the end of the presentation, I'll put some URLs into the chat, which have some articles that go over the development of the control system, which I find quite interesting. The test day procedure itself is relatively simple. We provide them a bunch of information prior to going. This includes car track width and wheelbase and our approximate unsprung masses. And we bring the car to the facility on the day, and we plonk it onto the rig as shown there. We also fill it up with a bunch of ballast as well. In our case, that was quite a considerable chunk, around 150 kilos worth. But that was just because we were taking a rolling chassis rather than a complete car. But the ballast is usually there to account for the driver mass as well, because you can't have them in there whilst they're shaking it. Else, I think they start to complain after a few runs, really. Various accelerometers and potentiometers are fastened onto the car and then connected to their data logging. The reason why it's only accelerometers and potentiometers is the maths around trying to model the suspension system. It can all be modeled using displacement alone, because the equation for velocity is the rate of change of displacement, and the equation for acceleration is, of course, rate of change of velocity. So you can differentiate or integrate to get whichever values you want. And that's what sort of makes this tool very, very strong, is that it doesn't need very many sensors to get a very accurate picture of what your car is doing. The baseline sweeps are performed after that to identify the main weaknesses and a start point for our tuning. And larger weaknesses are outlined there as well. And sometimes if there's a drastic error, which thankfully for us there wasn't, we may need to do a bit of restructuring, really. But then after you change a certain parameter, further test sweeps are done, and this is just iterated over and over and over again. This is just a summary of the vehicle model they generate. They only make a half-car model with the data because, again, it comes down to time of crunching numbers, and the half-car model does a good enough job for it. Then from all this data, a frequency response plot is generated for each mode, and various performance indicators can be determined from the plots, which I'll go into some more detail about shortly. But our initial findings for the car were that our front and rear axle stiffnesses were quite excessive in all 3 main modes. Our hub phasing for the front and rear was not very good. This is just basically saying that in a given mode of vibration, the wheels are out of sync, and so that can create a bit of instability front to rear, can lead to either understeer or oversteer. The ride height control on both axles, but particularly the front, was quite poor. The contact patch load variations weren't great either. This sort of signifies that the wheel is either experiencing too much load when it's going into bump, or it's not following the ground surface fast enough when it's in droop. Our damping ratios in heave and pitch modes were quite low as well, and the input sensitivities for the car were very, very high. And here's just a little brief video of the car being shaken about, just so you can sort of see how that all operates. But they collate all of this information into a single performance index value, where the rig perfect value is 0. You don't want to reach that value because, as I mentioned earlier, that sort of suspension system feels really wallowy and vague. So you want to be in the region of 0.1 to 0.3. Looking at some of the plots that we've got as well. This is a 3D contour of input sensitivity for the springs. Effectively, what this is showing is a rough summation of how much performance is left to be gained by changing characteristics in that certain area. So on the left is where we started, and on the right is where we ended. The higher points where it's clipping are caused by us having too much preload on there. In fact, having preload on there full stop was causing a lot of issues. But the aim with these contours is to get them looking as flat as possible, so that you've extracted as much performance out of that component as you could. Similar thing can be seen with the damping there as well. We didn't manage to get it as flat. This isn't necessarily a bad thing, because what the slightly less flat shape offers is more adjustment range, and any adjustments you do make have a larger impact. So it's a bit of a fine balance, really. Going on to this initial graph of our contact patch load variation. This one shows the disparity between front and rear contact patch loads through the full frequency sweep of 0 Hertz up to 40 Hertz, I believe, is the cutoff point. If you look at the legends in the top right, zeta is the approximated damping ratio as a percentage of the critical damping at the axle. The amplitude value is the effective weight on the contact patch caused by the spring. So what we're seeing on this graph as well is, as the red and green plots deviate, that shows that they aren't very symmetrical in their contact patch load, so you're not getting even weight distribution across the car. That's not atypical, but it's more the shape of the graph which is the concerning part. You want those to be almost a mirror image, just slightly offset from each other. So that's the baseline value. The final value, as you can see, the graphs follow each other much more closely, and they've got pretty much the exact same shape. This indicates better load distribution front to rear, and also you can see from the legends in the top right, you've got an increase in the front and rear damping ratios at the axle as well, which is always a bonus. There is also a reduction in the natural frequency at the axle, which is quite useful because that's a good indicator to how stiffly sprung your car or bike is. This plot here showcases the tyre to strut deformation ratio. So what this is, it's effectively approximating the spring performance relative to the tyre. The front and rear tyre deflections per unit of spring deflection, which is the strut part of it, they are linearized and plotted through this frequency sweep here. The legend shows spot values as opposed to parameters. These are taken at the approximate heave mode resonant frequency. And what we want to try and avoid is high and low values of amp. If you're getting towards the 1.0 mark with amplitude, this tends to indicate that your springs are too stiff for the chosen tyres and they're working too much. So they're likely to overheat and break grip a little bit faster. Lower values, somewhere in the region of less than 0.25, this indicates that the tyres aren't being worked as much as you want, so they're going to have trouble reaching operating temperatures. Comparing that one to the final one we've got, there's a decrease in amplitude, which means that we're sort of getting into the sweet spot of around 0.3 to 0.4, around there. So our tyres are being worked a little nicer. They're not being under or overworked. And the phasing between the two responses is improved as well, so it's more even across front and rear axles. This graph, very similar to the first one I showed, but this is purely in heave mode. So this is showing, in the red plot, it's showing the heave mode response of the car on the suspension and the tyres. The green plot shows the response of the sprung mass only acting on the suspension itself. It's got the same plotting method as the contact patch load variation. And again, it's got the value of zeta in there. This time it's approximating the heave mode damping ratio. Now, this is only an approximation, as the filter to linearize these numbers is only bipolar, and is effectively acting as a linear mass spring damper system, whereas the real car will have at least 8 degrees of freedom. So taking these performance metric with a grain of salt is relatively important, I think. But comparing it to the final values, again, it's a case of there being better similarity between the two. So your suspension stability in that aspect is sort of increasing a little bit, and the damping ratio has increased again as well. This final set of plots I'm going to show you is a rough approximation of suspension performance. It's defined by Multimatic as a reasonable estimate of suspension performance, that being the combination of springs, dampers, and the geometry itself. The limitation with this is that the plots aren't atypical, and they can't be trusted below frequencies of about 3 Hertz. As our car is quite stiffly sprung and our natural frequency is in the region of 4.1 Hertz, that's not necessarily an issue. But what needs to be taken into account is any sort of response plots backwards of 3 Hertz aren't very accurate, really. And again, spot values are taken at the approximate heave mode natural frequency. The performance parameters we're sort of mainly looking at with these plots is the phase angles in particular. Angles of about plus 50 degrees indicate that the springs and dampers are well matched. If you start to go lower than 50, you're looking at more of a spring controlled system, which means that changes in your dampers won't yield as much performance increase. Going higher than that means that your dampers are controlling the majority of the suspension performance. So changes in your spring rates aren't going to do as much in that sense. The plots above are ones of a spring limited system. This is where we were at first, and where that point of having any preload on the springs tends to knacker the actual performance metrics of your car at that point. Then these are the final plots. We are seeing a nice increase in the phase angles particularly. This just sort of means that we're getting closer to the optimum value of 50, which means the performance increases from our springs and dampers are sort of combining nicely. And they're now starting to become a little bit more matched. Then just to summarize all of our key performance indicator improvements, we've seen a 38.4% and 44% increase front and rear, respectively, of the axle damping percentages. We've seen a wide variety of increases in modal damping as well, 59% in heave, 57.5% in pitch modes. The contact patch load variations are reduced quite significantly in the front and rear, which sort of gives an indication that the front and rear loads are more balanced. The car's going to be a bit more stable through corners and on the brakes too. Gross axle heave stiffnesses have been reduced as well. This might seem counterintuitive for a performance vehicle, because the sort of common consensus is that a stiffer sprung car is a better car. That holds true up until a point. If you're way too stiff, of course your tyre is going to get worked way too much, as I showcased in those plots back there. So in our instance, we wanted to reduce the actual stiffnesses to let the suspension be a bit more compliant and do more of the suspending work to leave more room for the tire to do its own thing. Then tire to strut deflections on the front and rear have been reduced significantly as well. Again, it's a showcase that the tires are being worked less and the suspension is doing more of the suspending work. Then sort of the main one, which I'm very interested in, is the front and rear hub phasing disparities. It's bringing the front and rear oscillations and responses closer together to make both the front and rear end mirror each other better and basically make the entire car feel a bit more planted and stable. Then our performance index dropped from that initial 3.8 something value down to 0.475. We're not quite in that region of 0.1 to 0.3 that we'd like to be, but I think that improvement is relatively big, so I'm pretty happy with all of that information as well. Just a quick note as well, visual analysis of the car on the rig is useful, particularly if you see where the car starts to enter its natural frequency there. The effects of the vertical bump steer are sort of shown quite largely here. You get a lot of deviation side to side of the wheel. We found out that the actual steering geometry compared to the suspension geometry wasn't ideal. So we're putting in measures now to sort of try and reduce that. As well as that, the warp test was performed and we saw that the front hoop was flexing almost too much really. So what we found out was that the load paths of the suspension at the front were acting into weak points of that front roll hoop. So I'll go over this in our future plans portion, but that's something that we're trying to mitigate here too. And in the sort of very extreme ends of the frequencies, where you're approaching your natural frequency of the entire system, if your car is over damped in rebound, you can start to quite clearly see that the wheels are skipping off the pads. And that's sort of a very good visual indicator that there's something quite wrong in that area. But just looking at the car on the rig can tell you a surprising amount, really. So that sort of leads us on to what the future plans of the team are. Currently, as part of my own thesis, I'm developing an anti-roll system. Originally, the geometry of the car wasn't made to integrate an anti-roll system, but we found that from a lot of the data we gathered, the roll control can be sort of semi-separated from the dampers if you've got a separate spring, i.e. an anti-roll bar there. However, it doesn't really let us control damping in roll mode oscillations as well. That's where you'd be looking into a third element system or a heave spring and a split mode suspension system. The front installation stiffness improvements, that's to do with bracing the front roll hoop to stop the lozenging and the flex really. And as part of the 2023 Formula Student Financial Award, which we've been successful with, we're going to do an investigation into the performance impacts of hysteresis. We've been awarded £3,500 to spend on a set of dampers which Multimatic themselves make specifically for Formula Student. The main difference being that the internal valving between the ones that we're planning to buy and the Öhlins dampers we're using is completely different, and that's where the investigation into that is mainly headed. So I just want to thank everyone for listening as well. It might sound like I've been rambling a lot, but like I say, I'm not a professional, but this learning experience that we've had with Multimatic has been really useful, really. But yeah, feel free to ask any like questions that you might have in the chat. And I'll get those URLs for those articles too. But yeah, I hope you guys enjoyed it, and yeah, I guess I'll hand over to Graham for the final part.
Okay, thank you, Tryggvi. That was really good. I found that really interesting, very informative, and I think you've done a great job in presenting the work that you've done there. I've just got one question, and then I'll open it up to the floor. Well, a couple of questions actually. Just thinking about the last thing you talked about, the active anti-roll system. Well, the anti-roll system, is that going to be an active system or something that you tweak as and when you develop your system?
So per the rules of the Formula Student competition, we're not allowed any active suspension systems. So it will be it's going to be a case of a manually adjustable anti-roll bar, really. So, but what we're aiming to achieve with that is just trying to sort of separate the modes of oscillation, so you can tune each one separately. That's sort of a flaw with the four corner system, is that all of the springs act together in all three modes. But if you add a second element in there which only acts in one of those modes, you can sort of tune your parameters in that sense for that one region. So that's where the integration of the anti-roll system sort of comes into play. In terms of the actual system we're implementing, it's going to be a simple U-shaped bar, but the investigation is really going to be into the frequency response and how we can generate a approximate mathematical model to sort of try and mathematically predict where we want the adjustments to be and what sort of values we want.
Okay, that's great. Thank you. I think I'll hand you back to Sarah now, who may have some questions from the rest of the audience before we go any further. Can you take over from here, Sarah, please?
Yes, no problem, Graham. We haven't got any specific questions that have appeared in the chat. There's a couple of comments of people wanting to thank you, Tryggvi, for your excellent presentation. If anyone does have any questions, please feel free either to ask them out loud or to drop them in the chat. Just while we're doing that, I'll just take over again, Tryggvi, and share my presentation. I can just point out a couple of events that we've got coming up in the future. We do have a seminar taking place at IAPS, which is connected with the University of Bath. It's just north of Bristol, their base. That's a net zero vehicle engineering, design and development technologies seminar. So that is available for you to book now, and there are further details on our website. Also of interest might be our instrumentation analysis and testing exhibition, which takes place each year at Silverstone. That event is in the planning stages, and you are able to register free of charge for that event now. And we are still accepting abstracts for our Fatigue 2024 conference, which takes place in Cambridge next summer. We've got other events that are potentially in the pipeline, including we're hoping to run something in June on high integrity structural joints. And again, in July, we're hoping to have an event on battery testing. So if you are interested in attending any future events, please do keep your eye on our website, or if you're not on our mailing list, let me know and I can add you to that so you hear about things. So there's no further questions that have come in, Graham. So I don't know if we want to wrap up now.
One question has actually just come in from Jeremy Allen, asking why we selected a steel chassis. Yes. The main reason we went for a steel chassis is mostly from a cost and simplicity aspect. There's a lot of structural documentation and safety procedures which go into making a chassis for this type of car, mostly because ultimately it's a bunch of students making a car, so it's very much a case of you have to take a lot more care safety wise. But with making a steel chassis, it's very much a case of it's simpler to make, and doing a lot of the FEA and analysis for it as well tends to be a little easier. But then from, of course, the boring insurance perspective, really, if you've got students who have no real accreditation or like sort of codes involved with making a composite tub. If something bad happens to them on track, it becomes a very big issue for both the university and the people running the organisation as well. So whilst it would be beneficial both in terms of torsional stiffness and weight to go with a composite tub, it's not really feasible in our time frame, along with the fact that our team is only 12 people to 14 people big. So there are a lot bigger teams that have at least that number of people working on the chassis alone and doing all the theory work around making a safe tub. So a steel chassis really is the one that made sense to go with. But as I briefly mentioned, the optimization we've done to make it as stiff as possible has sort of paid off, really.
Yeah, I'll finish off then, if there's no more, with one non-technical question. How do you choose from your team the driver is going to drive the car, get the fun part of it?
Well, that's sort of I think that's more of a question of commitment, really. I mean, there's rules around being legally eligible to drive the car. Of course, you have to have a driver's license, and it has to be a UK Class B license or an international equivalent. But it's very much a case of if you show up into the workshop and get the work done and put in time outside of your course to help with it, then you're pretty much chosen to be a driver. It's all well and good to be wanting to be part of the team and just want to show up and drive, but that's not where the majority of the hard work is. So it's very much a reward to drive the car rather than just being something that you're sort of handed, really.
Mm-hmm. That's great. Anyway, thanks. Really good presentation, Tryggvi, and all the best of luck with your team, and in particular with your studies and your final outcome when you go out into the real world of motorsport.
Thank you very much, Graham.
Graham, just one, we have a follow-up question from Jeremy. All good reasons, he says. Was it heavier than carbon composite?
But we managed to optimize all our tube structures to get our current steel chassis to around 31 kilos. And that's down from about 42 kilos on the last generation car too. So it is heavier, yes, but the margin to which it is heavier isn't drastic. And we've tried to get it as light as we physically can.
Okay, thank you, Tryggvi. I think we can finish off there. Okay, Sarah?
Yeah, that's fine. Thank you everyone for joining us, and if you'd like to hear about further events for the IS, do ask me to add you to our mailing list if you're not already on. Thank you and enjoy the rest of your day.